Another concept that is going to help us graph functions, and we're going to use derivative of functions in order to find that, is concavity, points of inflection, and finding points of inflection. The objectives is to determine the concavity of a graph of a function at a point, find points of inflection of graphs of functions, to use the second derivative test to graph functions. Assume that the first and second derivatives of function f exists. The function f is said to be concave up on an interval I if the second derivative of x is greater than 0 on that interval, and it is concave up at a certain point a and off of a if f double prime of a is greater than 0, or the second derivative is greater than 0. The function f is concave down on an interval I if the second derivative of x is less than 0 on that interval, and it is concave down at a certain point a and f of a if f double prime of a is less than 0. Here's an illustration of concave up and concave down. When we say concave down, we mean that the graph of the function forms a mountain. When we say concave up, we mean the graph of the function makes a cup or a valley. Let's look at the first example. Is the graph of the function f of x is equal to x cubed minus 4x squared plus 3 concave up or down at the points a, 1 and 0, b, 2 and negative 5. To find out whether it's concave up or down, we have to find f double prime of x. Basically, we're going to find the first derivative and then differentiate the first derivative to find the second derivative. So the first derivative is 3x squared minus 8x. The second derivative is the derivative of the first one, which is 6x minus 8. We're going to test the second derivative at the points given in the question. So the first point is 1 and 0. We're going to plug 1 and 0 in the second derivative. Let me fix that. This is basically the second derivative, not the first derivative. If you plug it, you're going to get 6 times 1 minus 8, which is negative 2. Negative 2 is less than 0, so that the graph is concave down. Let's test the second point. If we have 2 and negative 5, we're going to plug 2 into f double prime of x, f double prime of x. So you're going to get 6 times 2 minus 8, which is 4. That is greater than 0. That means the graph is concave up. Looks like a cup. Points of inflection. A point x0, y0 on the graph of a function f is called a point of inflection if the curve is concave up on one side of the point and concave down on the other side of the point. In other words, the second derivative at the point of inflection is going to be either equal to 0 or undefined, and this is called the second derivative test. The procedure. To find the points of inflection of a curve and intervals where it is concave up and where it is concave down, first we need to find the second derivative of the function. Next, we're going to set the second derivative of the function is equal to 0 and solve for x and find any points that make the second derivative undefined. Next, we're going to find the potential points of inflection by plugging the points resulting from step number 2 into the original function and solving for y. The fourth step is if the second derivative has the opposite sign on the two sides of one of these values of x, a point of inflection occurs, meaning we need to test the intervals created by those points resulting from step number 2. The curve is concave up where the second derivative is positive, and it is concave down where the second derivative is negative. The change in sign of the second derivative corresponds to changes in concavity and occur at points of inflection. Let's look at this example. We want to find the points of inflection and concavity of the graph. Y equals 1/2 x to the 4th minus x cubed plus 5. The first step is to find the first derivative and second derivative. So after we find the second derivative, we're going to find every point that makes the second derivative undefined. I don't see any here since we don't have denominators or radicals. So we're going to find every point that makes the second derivative equal to 0. I'm going to set it equal to 0 and solve for x. I'm going to take 6x out as a common factor. So I will get 6x times x minus 1 equal to 0 and then solve for x. I will get x is equal to 0 and x is equal to 1. I'm going to find potential inflection points by plugging x is equal to 0 and x is equal to 1 into the original function and finding the value of y. So if I do that, I will get 0 and 5, and I will get 1 and 9 over 2. And those are potential inflection points. We have 3 intervals to test. So let's create a sign diagram. Namely, those intervals happen at the first point that we got from step number 2, which is 0 and 1. So we have 3 intervals from negative infinity to 0, from 0 to 1, from 1 to positive infinity. If we create the sign diagram, we will get the intervals. So we have negative 1 from the first interval, 0.5 from the second interval, and 2 from the third interval. If you plug negative 1 into the second derivative of the function, you'll get 12. That means it's positive. And since it's a positive number, the function here is concave up. So it is concave up like that. If we plug 0.5 into the second derivative, we get negative 1.5. Since it's negative, the function is concave down. And if you plug 2 into the second derivative, you get 12. It's positive, so the function is concave up. Last but not least, an application example. Suppose that Sunglasses Hut Company has a profit function given by P of Q is equal to negative 0.03Q squared plus 3Q minus 36, where Q is the number of thousands of pairs of sunglasses sold and produced, and P of Q is the total profit in thousands of dollars from selling and producing Q pairs of sunglasses. We want to find a simplified expression of the marginal profit function. And we want to find how many pairs of sunglasses in thousands should be sold to maximize profit. What are the actual maximum profit in thousands that can be expected? There is a typo right here. This is maximum. We know that the marginal profit function is the first derivative of the profit function. So we're going to find the first derivative. P prime of Q is equal to negative 0.06Q plus 3. And that is the simplest form of the derivative or the marginal profit function. Next, we want to find the number of sunglasses that should be produced in order to maximize profit. In this case, we know that if we put the derivative is equal to 0, we're going to get a potential extrema. And then we have to test whether this extrema is going to be a relative maximum or a minimum. So to do that, we're going to put P prime of Q is equal to 0 and solve for Q. When we solve for Q, we get Q is equal to 50. But is that Q equal to 50 a maximum or a minimum? Let's use the second derivative test in order to determine that. We're going to find the second derivative. So if you find the second derivative, you will get P double prime of Q is equal to negative 0.06, which is the derivative of the first derivative or this first derivative. Now we know that P double prime at 50 is equal to negative 0.06 still. So if the second derivative is less than 0, that means the function is concave down. If it's concave down, then we're going to have a maximum at that point. So this means 50,000 sunglasses should be sold to maximize profit. Next, we're going to find the maximum profit, the actual maximum profit. Since a production of 50,000 sunglasses will maximize the profit, we can find the profit using the profit function. So we plug 50 into the profit function, so we get P of 50 is equal to 39 thousandths. The maximum profit is $39,000.